Welcome back to my channel Chemistry Unplugged. Today we will discuss about problems from CSIR NET and GATE on the topic organic reagents, lithium ammonia, basically Birch Reduction, Bu3SnH Silanes and Hydride transfer reducing agents like lithium aluminum hydride and hydrides of sodium borohydrides. This is the first question from CSIR NET December 2011. So in the first step, we are using N-bromosuccinabide, which is NBS, and it is source of Br+ ions, and they will attack first on double bond of this ester. Now in the second step, we will use this alcohol, and the lone pair of this alcohol or this OH group will attack on the more hindered side of this carbon. It will attack on this carbon. It is more hindered, attached with OET group, and Br will shift here. It has positive charge, so this bond will shift on bromine. We have this structure, so always remember this. In case of NBS, when we have alcohol, then alcohol will attack on the more hindered side of alkene. So this will be the product A. Then we are using Bu3SnH in presence of AIBN. It is an initiator, we know that, and benzene as a solvent. So in the first step, this Bu3SnH bond will break and we have Bu3Sn radical. And this radical has a strong affinity for halogens like Br. So it will attack on it and this Br radical will be removed. And we have a radical on this carbon. Now in the second step, this radical will attack on this double bond and it preferentially forms 5-membered ring. We have already discussed about it. So a 5-membered ring is formed and we have a radical here. Now this H radical, which is formed after the photolysis of this, will attack on this carbon and we have the final product. This is the final product B. Next question is from June 2012, and first we are using PPH3, DET and 2-iodophenol. DET is diethyl azo dicarboxylate. So in the first step, PPH3 will attack on DET, diethyl azo dicarboxylate. So it will attack on the nitrogen of DET. The lone pair of electron on phosphorus will attack on nitrogen, and this double bond will shift on this nitrogen. So it has negative charge. So we have this intermediate here which will abstract hydrogen from 2-iodophenol and generate a nucleophile. We have this 2-iodophenol molecule and this negatively charged nitrogen will abstract hydrogen from it. So we have a nucleophile here. We will use it later. In the next step, we have this dead molecule with PPH3 group and 1 hydrogen on the nitrogen. Now, in the next step, the radical present on the oxygen of this alcohol will attack on this PPH3 and we have this intermediate. Now, this bond will shift on nitrogen and it will be, now the nitrogen has negative charge. In the next step, this negatively charged nitrogen will abstract this hydrogen. Now we have this oxygen group attached with PPH3 group, because we know that it has a strong, PPH3 group has a strong affinity for oxygen. In the next step, nucleophile will attack on it and this is our nucleophile. So it will attack on this carbon atom and this bond will shift here and PPH3O will be removed. And this is SN2 reaction, so there will be inversion in configuration. So if this group is above the plane, then this group, this nucleophile will attach below the plane. This will be the structure. So this is the compound A. In the next step, we are using tributyl tin hydride. So first step is the homolysis of tributyl tin hydride and tributyl tin radical will attack on iodine. It will attack on iodine and we have our radical on this carbon atom. Now this radical will attack on this double bond and 5-member ring formation is favorable. So suppose this group is below the plane, then the hydrogen attached on this carbon will be above the plane. Okay, if one group is below the plane, the hydrogen will be above the plane. So when this radical group will attack on the alkene, it will also attack from the lower side. So it will also go to the lower side of this carbon, and this methyl group will be above the plane. If you have to remember this, determining stereochemistry, if one group is above the plane, other will be below the plane. So this is the structure. This group will also attach on the lower side of this carbon atom. Now we know that the hydrogen will be on the side, our side, if this group is below the side, and the methyl group will also be above the plane. This is the P, but this double bond should not be there. It is a mistake, so you have to remember this double bond after bond formation. It should not be there. The next question is from June 13. We are again using tributyl tin chloride in this case, and sodium borohydride and Jones reagent. So first step, we are using tributyl tin chloride and sodium borohydride. I have discussed it in the video on tin hydride that for the limited supply of tributyl tin radical, we can use tributyl tin chloride with sodium borohydride. So it generates tributyl tin hydride in limited amount, and AIBN is an indicator here. If the concentration of tributyl tin hydride is high, so the ring formation will not take place. So it should be in limited amount for efficient reaction. So this radical will attack on this bromine, and we have a radical on this carbon atom. Now this radical will attack on this carbon to form a 5-member ring. Now H radical will attack on this carbon. We can also write it down like this, because if one bulkier group is above the plane, other will be below the plane, to avoid steric hindrance. So it can also have a structure like this. Now we are using H2SO4 and CrO3. It is also called as Jones reagent. We have also discussed about it. So it can convert this OET group first into alcohol, and then this secondary alcohol will be converted into ketone. So this will be the final product. Next question is from December 2013, and you have to identify A, B and C. So first take A. A converts this, reduce this double bond only, so we can use only lithium ammonia. Sodium borohydride with cerium chloride cannot do this function. It is Birch reduction, and it can reduce only C double bond O without affecting this bond, carbon-carbon bond. So A and B can be the correct answer. Next is B. B is sodium borohydride and cerium chloride. It is Birch reduction, and it reduces C double bond O without affecting this double bond. Alpha beta unsaturated double bond is unaffected, and only carbonyl is reduced to OH. So now third is the reduction of this double bond. Only the ring double bond is not reduced. It can only do by Wilkinson catalyst. We have discussed about it. So the option A will be the correct answer. Next question is from again December 2013. We are using tributyl tin hydride and AIBN, which is an initiator for generation of tributyl tin radical. So we have a tributyl tin radical here. It will first attack on this bromine. Okay, so we have one radical here on this carbon. So now this radical will attack on this double bond. So if this group is below the plane, then the hydrogen present on this carbon atom will be above the plane. Okay, and this group is below the plane, so the radical will also attack from the side which is below the plane. So the hydrogen present on this double bond carbon will be above the plane. Okay, so in the first step this will attack here, and we have radical on this. So we can also write it down like this. Both groups are below the plane and hydrogen is above the plane, and hydrogen placed on this carbon will be above the plane. Now in the next step, this cyclopropane ring will break, and here is the formation of double bond. These two radicals will combine to form a double bond. If this hydrogen is above the plane, the carbon chain attached with ester group will be below the plane. Always remember, if one group is above the plane, other will be below the plane. So this will be the structure. Next question is from June 14, and tributyl tin hydride and AIBN is used. So it is very important reagent. It has been frequently asked in the exams. So first step is the formation of tributyl tin radical, and this radical will attack on bromine, and we have radical on this carbon atom. This is the structure, and if this group is above the plane, then the radical will attack on the alkene also from the side above the plane. So the hydrogen will be below the plane. So if this group is above the plane, the hydrogen will be below the plane. Now this radical will also attack from the side above the plane. This radical will shift on this carbon, and we have this structure. Now the hydrogen attached on this carbon will also be below the plane. Now this radical will combine with triple bond to form double bond, and this hydrogen, because this hydrogen is above the plane, then this group will be below the plane, and the radical will also attack from the side below the plane, and the methyl group will be above the plane. So this will be the structure, and it is the final compound. Now in the next question we are using Birch reduction. In Birch reduction, electron withdrawing groups show ipso and para reduction, and the alkynes are converted into alkenes with E configuration. E configuration is preferentially formed. So in the product we have, this is the ipso reduction, and this alkyne is converted into alkene with E configuration. Next question is from December 14, and we are using TBAF. TBAF is tertiary butyl ammonium fluoride. So in the first step we are using tertiary butyl ammonium fluoride. So this fluorine is acting as a nucleophile here, and it will attack on trimethylsilyl, because we know that silyl group has strong affinity for hard nucleophiles. So it will be removed, and this bond will shift here, this bond will shift here, and this double bond will shift to nitrogen, electronegative nitrogen. Now nitrogen has negative charge in this structure. Next we are using an anhydride containing an alkene group also. So this bond will shift here because of the presence of ester group here, strong electronegativity, and this negative charge of nitrogen will attack on this electron deficient carbon. So we have this group attached on this nitrogen atom. Now it is the product A, and now we are using heat. We are heating it, and we can see that here we have a diene and dienophile. So it is a 4+2 cycloaddition. So this bond will attack here, this bond will shift here, and this pi electron will shift here. So here is the formation of one 6-membered ring by cycloaddition. 4+2 cycloaddition leads to formation of 6-membered ring. So it is attached here, and the above side portion is also a 6-membered ring containing nitrogen carbonyl group. So, and here we have carbonyl group. So this is the final product. Next question is from December 14, and we are using DIBAL, is diisobutyl aluminum hydride, and we are using it at -78 degrees centigrade. So it will convert carbonyl group into alcohol, and because it is a bulkier hydride transfer group, so it will attack from the side which is less hindered. If these hydrogens are below the plane, then this group attached with dimethyl group will be above the plane. So the DIBL will attack from the side below the plane, then OH will be attached above the plane. So because of the presence of these two methyl group, the hydride will attack from the less hinder side. Then we are using dead end PPH3. In the first step, PPH3 will attack on diethyl azodicarboxylate. So it will attack on nitrogen. This bond will shift here. So this PPH3 group will attach here and we have negative charge on this nitrogen. Now we will use monochloroacetic acid. So this negatively charged nitrogen will abstract its hydrogen and there is the formation of nucleophile, monochloroacetate. We will use it later. In the next step, this alcohol group will attack on PPH3. So it will attack on this positively charged phosphorus. Then we have positive charge on oxygen and this bond is shift here. I am showing it in the first one step that this bond will shift here. Nitrogen has negative charge. Now this hydrogen will attack on this negatively charged nitrogen and we have now in the next step we will use our nucleophile monochloroacetate. So it will attack on this carbon atom and it will show SN2 mechanism. So it is inversion in configuration and this bond will break, attach this group here. Now the hydride ion will attack on this carbon atom and it will attack from the side which is less hindered. So it will attack from the side above the plane because this group is below the plane. So the H will attack from the side above the plane, then OH will be below the plane. So in the product OH will be below the plane. Then the next example is again from December 14 and we are using 4-methoxybenzaldehyde in acidic medium and DIBAL at low temperature. So in the first step we have 4-methoxybenzaldehyde. Now because we are using acidic medium, so this H plus will attack on oxygen of carbonyl group. Now this group will attack on the reactant and this bond will shift here and the lone pair present on oxygen will attack on this carbon atom. And we have a structure like this. This group is attached here. And in the next step we are using H radicals. Again they will attack on OH group to form OH2 plus. So we have this and it is a good leaving group. So OH2 will be removed and we have positive charge on this carbon atom. So the lone pair present on oxygen will attack on this carbon atom and we have a structure like this. Here is the formation of dioxane. In the next step we are using DIBAL. So it can reduce its dioxane group into alcohols but it will not affect triple bond. So this bond will break from here and we have this as a final product. Here is the attachment of OPME group, OPMB group, PMB for para-methoxybenzyl group and the triple bond will remain unaffected. This is the final product. Now in the next step we are using sodium borohydride with cerium chloride is this Birch reduction and we are also using here methanol and we have two groups here, ketones and aldehyde. So this sodium borohydride will reduce ketone to alcohol but because of the presence of methanol it will not reduce aldehyde. Aldehyde forms methoxyacetal with methanol. So it will not show reaction with sodium borohydride. Only the ketone group will be reduced. So in presence of methanol, aldehyde group cannot be reduced by sodium borohydride in cerium chloride solution. So this is the final product. Next question is also from June 2015 and we have this reactant and we are using sodium borohydride in methanol. So it is very easy question. We have two methyl groups. So hydride will attack from the side which is less hindered. KF side is less hindered and U-shaped side is less hindered. So hydride will attack from the axial side and there is the formation of equatorial alcohol and acetate group will not be affected. In the next question we are using, it is a hydrazine of paratoside. This is very important reaction. First is the formation of hydrazone using hydrazine and this carbonyl group. So this hydrazone will be formed and now we are using NaBH3Cl. It is less reactive as compared to sodium borohydride because of the presence of electron withdrawing CN group, and it can reduce it in presence of protic solvent. So this group will be removed and we have a carbon here. So it is basically conversion of carbonyl group into hydrocarbons. Acetate group will be unaffected, double bond will be unaffected. So that's it. I will end my today's video here. It is the first part of this solve question problem series, and please subscribe to my channel and press the bell icon for future notification. I will soon upload second part of it. Keep watching my channel. Thank you so much.